Thank you very much. Now that Paula has told you much of astrochemistry, okay, so I can't walk around. That's my normal style. All right. Anyway, now that Paula has told you in a very beautiful talk much of what is astrochemistry is about, my job is easier for me. I'm only going to make the introduction to the first of three sessions, and these three sessions will give you, I think, a better flavor of the whole field. And what we're starting off with is, in the chemistry of space, novel chemicals and reaction mechanisms. I think you've heard quite a lot about this already, and this will be maybe a little more detailed and more specific. So I didn't start with the Milky Way. I'm starting with the Andromeda galaxy here, because it gives you a better picture of what a spiral galaxy is like. And perhaps 90% of the matter in this and other spiral galaxies of the type is in the form of stars. And you can see the stars, they're hot, they're bright, and so the eye sees them in the visible. The interstellar medium, the clouds in the interstellar medium can be much more difficult to see because they're, in general, except for star formation, very, very, very cool, and so have to be studied at longer wavelengths. Okay. So again, I start with the black cloud. Actually, Ted Bergen has studied this cloud a lot. This is a very nice picture. It's spectacular in the sense that very little visible light comes through this cloud. So it has to be studied spectroscopically at longer wavelengths. And longer wavelengths means both rotational spectroscopy and vibrational spectroscopy. And most rotational spectroscopy can be done from the ground, so it's an easier technique than the infrared spectroscopy. So unlike the chemical laboratory in which infrared spectroscopy is the more important of the two, much of what we see in space comes from the what astronomers would call the radio astronomy, which is really from microwaves to submillimeter waves. Infrared astronomy can be done partially from the ground using sources like this, a stellar continuum background that can go through. The problem is our own atmosphere for the most part. There's a lot of water vapor even at the highest elevations, and so we often, need and often have one infrared telescope in space. We soon will have another one that will tell us a lot more about the infrared molecular universe. Two things to note about these. This is a cold, dark cloud, temperatures between, say, 6 and 10 Kelvin. We also have to be careful, by the way, in clouds, they are not really often in thermodynamic equilibrium from the chemical point of view and from the physical point of view. And the dust particles often have different temperatures from the gas. So not worrying about these differences, anyway, these are quite cold, these regions. It is where molecular hydrogen is made, and under interstellar conditions, the only way to make molecular hydrogen from two hydrogen atoms is by what's called a radiative association. I'm sorry, in the gas anyway, and that is very, very slow for H plus H. The idea being the two hydrogen atoms mostly just hit each other and then come apart. So what happens is they can be made on a surface because the surface of a grain can be thought of as a third body. And this third body can take away the excess energy once molecular hydrogen is formed temporarily on the surface of a grain by diffusion. And the other important thing is, again, as Paula mentioned, cosmic rays that do cause in the gas phase mainly ionization. And this leads to a rich ion-neutral chemistry. All right, so rather than show you again the picture of all the molecules, I thought I'd just group these interstellar molecules into various types. So this doesn't mean that all come from one source and all come from another source, but just these are types. There are lots of simple species. So the most abundant is hydrogen. The next most abundant in the gas is carbon monoxide. And we see the ion H3+, just reminding us that space is a weak plasma, even if it has a temperature of 10 Kelvin. All right. Then we have some very exotic molecules, and here are some very interesting ones. These are called carbon chains by astronomers. They're just polyines are related to polyines by chemists. So they're very weak in hydrogen, so totally unsaturated. And you would look at them and you might not even believe some of them could exist. So, for example, C4S, who would even know what HNCCC means? Actually, it means what the structure looks like, what it says. This is a very strange isomer of cyanoacetylene, which has other strange isomers. And then we have radicals missing a hydrogen at one end. We have negative ions in the gas phase in space. So we have 3-membered rings, which I haven't shown. So there's a whole pool of exotic molecules. And as I tell students, there is no octet rule in space, so, to put it strongly. All right, then we have normal molecules called originally complex organic molecules. They're organic, but they're certainly not complex by chemical standards. And so they're rather ordinary. You find them all in an organic laboratory. And we start from 6 atoms, so that puts methanol in. But the ones that are talked about the most are dimethyl ether and methyl formate, because they each are internal rotors. And so rotational spectroscopy gives us thousands of lines in some of the warmer sources. So they are very abundant, at least spectroscopically, and well studied. The complex molecules are the fullerenes, and even a fullerene ion, which is rather unusual, and the polycyclic aromatic hydrocarbons. The PAH hypothesis, it's more than a hypothesis, comes from aromatic features. Individual polycyclic aromatic hydrocarbons have not yet been detected. The closest we come is to monocyclic polycyclic aromatic hydrocarbons, and that's benzene and much more recently cyanobenzene. There are lots of unidentified molecules in various clouds, even in diffuse clouds, which you can see through, called the diffuse interstellar bands. So hundreds of them still unidentified. This is all in the gas phase on the ices, as was brought out by Paula. We don't really have very high sensitivity in the infrared for ices. Of course, we can't see ices in the microwave. They don't rotate. And for the most part, they don't rotate. So we look at vibrational spectra, and then we can see only the most dominant. And so we don't see any exotic species, which no doubt are there, especially in cold sources. Okay, so another picture showing you, this is my version, showing you the different types of evolutionary stages, or interstellar medium stages, that one goes through, that the stars go through in the formation process. When they start from old stars, it's very important to think of this as a cyclical feature. And old stars, by explosive mechanism, or more gentle ones, give forth a variety of gas molecules and atoms and dust particles. And very soon afterwards, as we'll hear, one has very complex molecules, so the fullerenes, and then presumably they're tied up chemically within the PAHs. The diffuse clouds, which are very, well, more diffuse than the dense ones, typically 100 Kelvin or so, and a density of let's say, also 100 per cubic centimeter. It's actually, as an aside, very interesting that astronomers still use the CGS system. You can go from light years to cubic centimeters. But okay, anyway, so these densities are quite low. But still, although there are lots of small molecules, one still sees C60 plus in these regions. So any idea that we fully understand the chemistry that goes on in some of these sources is not completely correct, to put it mildly. Anyway, the diffuse clouds, some of them collapse into dark clouds or dense clouds, portions of which are like this small black cloud. Density is, as I said, 10 to the 4th. Temperatures, say, 5 to 10 Kelvin. And you would think, if you read any chemistry book, I would think, before astronomy became part of chemistry, you would say that you can't possibly make molecules under these conditions. Temperature 10 Kelvin, density 10 to the 4th. You don't have collisions very frequently. On the other hand, astronomy there has long time scales, and you make lots of molecules under these conditions. So it's very important, I think, what astronomy has done to change chemistry, especially low temperature kinetics. So cold sources like this have been associated with exotic molecules, The so-called complex organic molecules, until recently, have been associated more with warmer stages leading to star formation. But now, in the last decade, some of these so-called COMs, or complex organic molecules, have been seen in these cold sources. And that is still a mystery. We don't really get it right yet. All right, a little bit of chemistry. I had a feeling that Paula was going to use the slides she did, so I thought I'd look at it differently. Why do we make unsaturated species? How do we make unsaturated species? Well, here's an example. It's not quite 100% right, but it shows the flavor of the thing. So we're going to start with methane, and methane is presumably formed on grades and comes off non-thermally into a cold gas. C plus is a standard ion. And this is the reaction. Ion molecule reactions now have been well studied, thanks to the interest from astronomy, down to very low temperatures. Anyway, C2H3 plus can react with electrons. Reactions with electrons, it's called dissociative recombination because you don't form the neutral product, you form fragments. It was not really known what the products were until there was a lot of importance placed on it from astronomy, and we even had the use of partially defunct nuclear storage rings to use to study these reactions. And we found that the neutrals, the products are broken up often into three, or more than three products. So what happens now is you've gone from CH4, which is saturated, down to C2H. It's getting unsaturated. What would C2H do? It would react with C plus, make C3 plus, and you wouldn't have any hydrogen anymore. Now, this is not the only thing that happens, but it gives you a sense as you get to more complicated hydrocarbons, it's going to be mostly carbon. Right? Okay, and that's exactly what's seen. For longer species, it's very hard to put more than 2 hydrogen atoms on under these conditions. On the other hand, you can make ions, and this is another problem with ion-neutral reactions. The dissociative recombination is going to break things up, not only with hydrogen atoms coming off, but breaking other things. So protonated dimethyl ether does not lead to dimethyl ether. It says 7%, and the uncertainty is about 10%. So I don't know if it makes anything at all. Okay, so that's a problem. So people have recently gone back to neutral reactions. Now, astronomers are not as burdened as chemists with the fact that neutral reactions do tend to have activation energy. And activation energy is going to kill you, we thought for many years at low temperatures. Then it was found out that there are a lot of reactions between radicals and regular neutrals that don't have activation energy. And in fact, can get a little faster at low temperature than at room temperature. On the other hand, the OH plus methanol is one of these examples that has a big barrier and very slow at room temperature, and is basically 2 orders of magnitude faster under 100 Kelvin. And this is associated with tunneling, which has now become a rather popular subject. But it's not only tunneling. Tunneling would actually give you a temperature-independent region. And it's not, because it's not very temperature dependent on the conditions. So the potential surface, which seems to be, this is not the only case, has to first have a well to form a complex. And the longer the complex lives at lower temperature, the more chance it has to tunnel under the subsequent barrier. And that's the claim for this reaction. It's very important because the synthesis here starts with methanol and goes to dimethyl ether and methyl formate. Now, there's another problem here. According to this view, in order to make dimethyl ether, you have to have a methoxy radical and a methyl coming together by this radiative association mechanism, which I just said doesn't happen for 2 hydrogen atoms. Why would it happen here? Well, again, at low temperature, you wouldn't expect it by higher temperatures, but at low temperatures, complex could last a long time by standard arguments of unimolecular chemistry. And during that time, presumably by vibrational emission, stabilize itself. Has this been seen in the laboratory? No. Okay. It's very, very difficult because at most densities, the reaction goes by a third body. And of course, in space, we don't have a third body unless it's on a grain. So the gas phase, it's unclear. So we are trying to do a detailed calculation of this. It does happen in the ion neutral world because it's easier to study at very low densities in an ion trap. And the process does occur. All right, but does this make enough dimethyl ether and methyl formate to solve the problem of COMS at 10 Kelvin? Well, the paper that produced it said so. We couldn't reproduce it. And I don't think it works at 10 Kelvin. We can get it to work at slightly warmer temperatures. So other people have thought it might be surface chemistry. So you've seen this slide already. The surface chemistry, this is showing only the diffusion mechanism. Long-Hinchman mechanism is divided up. It's very temperature dependent. And above 20 Kelvin, molecules can diffuse on grains, come together by association, it's a three-body association, make larger molecules, and as the temperature goes higher, come off into the gas, as Paolo was saying. This doesn't explain everything, but it does explain much of it. At 10 Kelvin, on the other hand, the only things that really move are atoms, and hydrogen atoms in particular, because they can tunnel and they're weakly bound. And the only problem with that is very hard to make many bigger molecules this way. So there have been a lot of suggestions in the last few years, some rather fanciful in my view. So I'll start and end with one of them, which is I could call it fanciful because we've done it. And anyway, the strong argument against it, for it, is you'll hear that there are lots of laboratory experiments that do show that. So this is a computer simulation which took lots of memory of a big computer, showing what happens when a cosmic ray actually collides with an ice mantle. And what you see in those strange trajectories are secondary electrons coming off. Anyway, it leads to a solid ion molecule chemistry, which we very poorly understand, makes neutral species that are excited and very reactive. And the net result, assuming we have the chemistry at least approximately right, is we can make some of these, not all of them, but some of these complex organic molecules. So that's one of many possibilities that people are looking at these days. So I end with just a list of the 4 speakers in session 1. Mike McCarthy on exotic molecules, Catherine Walsh from across the pond, organic molecules and disks around young stars, which I didn't do, PAHs and fullerenes, more from Els Peters, and then the radiolysis or proton bombardment by Reggie Hudson. And thank you.